Bismillah ar-Rahman ar-Rahim. Last lecture we discussed how to implement a comparator, okay? A magnitude comparator circuit, okay? And we made a concrete example of having a 4-bit magnitude comparator. But the general idea is, the idea can be generalized to any number of bits comparator. So what happened is that we came up with some expressions, okay, using some logic, okay. We came up with expressions to tell us what is the so if we think about the comparator as a black box like this, and it takes A, which is 4-bit, and B, which is 4-bit, okay, and it produces 3 signals. Each one is 1 bit. GT is 1. If GT is 1, then we know that A is greater than B. If EQ is 1, then we know that A equals B. If LT is 1, and we know that A is less than B, okay? So this is what we call a black box description of the magnitude comparator functionality, okay? And we came up with, last time we came up with expressions for equal output, and we said that it is going to be the ending of all EI signals. EI is 1 if and only if AI, which is bit number I of A, AI is equal to BI. And bit number so if you add these together, you get EQ signal. And the greater than signal, GT, is going to be 1 if and only if A is greater than B, okay? Or in other words, if A3 is going to be greater than B3, in which we don't need to check anything else. If the most significant is of A is greater than the most significant bit of B, then this is sufficient for us to conclude that A is greater than B. Otherwise, if the most significant bits are equal, okay, then we check the next most significant bit. If the two, the most and next most significant bit are equal, then we check the next one, and so on and so forth, okay? So this is an OR condition, which results in this big expression here, okay? Similarly, for less than, we can come up with a similar expression like this one here, okay? Another way of doing the LT is that if we generate GT and EQ, then LT will be nothing but the NOR of GT and EQ. This is by logic, okay? If something is not greater than or equal to, it is less than, okay? So if we say A is not greater than or equal to B, then we know that A is less than B, okay? And we said that this is much more manageable than 256 rows truth table to deal with, okay? But now we discuss another way of designing the problem, designing the magnitude comparator, in which we say, well, hold on, I want to design my comparator in a bit slice manner. So I want to design a bit comparator, okay? I want to compare 2 bits if they are equal or greater than or less than, and then use this over all the bits of the numbers that I have. Okay, use this exact copy, okay, bit slice, okay, and cascade it over all the bits that I have. This is iterative design, and we did this same concept with the, if you remember, with the ripple carry adder, okay? The ripple carry adder, we did that. We designed the same cell, which is called the full adder, and then we cascaded it, okay, across all the cells. This is iterative design as well, okay? So now we are going to do the same for a magnitude comparator. So we are going to design a bit comparator and then cascade it so that it becomes n-bit comparator. Okay, so let me just illustrate what I want to do. Okay, so we want to design some black box here, which is, let's call it 1-bit comparator, 1-bit, yeah, we can call it magnitude comparator, and it takes AI, okay, because we can connect any bit of A to it, okay, and BI, okay, and then it compares them and produce some result greater than, less than, or equal to. But since we are using this at a local level at a bit, but the objective is to design a larger comparator, right? So we have to be able to look at what happened so far, the result of the comparison so far. So we must take the result of the comparison so far into account with the current input, okay? So we must take into account our greater than that is coming from the previous stage, okay, and equal and less than that is coming from the previous stage. And then, only then, we can generate our output, which is greater than and less than and equal and less than. Okay, so this is input and this is input, all 1-bit, input, 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 and output. Okay, output. In order not to confuse the this GT with this GT, we give them some indices. Let's say that this is GTI minus 1, okay? And this is EQI minus 1. And this is LTI minus 1, okay? And this is GTI, EQI, and LTI, okay? All right. Now, in order to illustrate what I mean by a bit slice, okay, let's take an example. Okay, suppose that my A is this number. Let's say that I have 0, 1. You just put in distanced and then 0, okay? And my B is going to be, so let me just pull these to the back a little bit. Okay? 1 and 0 and 1, okay? Before I do the comparison, using bit slices, what is your opinion about the comparison here? Is A greater than B or less than B or equal to B?
A is less than B.
Why is that? Because A
Because
is in decimal, it's 2, right? And B is 5, isn't it?
yes.
We know that 2 is less than 5. Okay, so what we do is that, okay, we start with these 2 bits, okay? And then have an initial GT, EQ, and less than. Initially, we say, well, we assume that the 2 numbers are equal. So my EQ will be 1, my GT is 0, and my LT is 0, okay? This is the initial state, okay? Now, I have assumed that the 2 numbers are equal, but I get now my A, okay, at this position, my A is 0, and my B is 1, even though they were equal from before, okay? From before, okay, they are equal. There is no before here because we know that, but at least we know that they were equal from this signal here, okay? So what is the output of this comparison here? Who can tell me what is the output of this comparison and why? This comparison is going to produce
0, 0, 1, because A is less than B.
excellent, excellent. 0, 0, 1, because A is less than B so far. Okay, so far we know that A is less than B. Okay, yeah, all right. Now we take this into consideration for the next stage. We take this input into consideration into the next stage. Okay, so now we use the same logic to compare the two bits and take this input into account, this input here into account. All right. So for this position, uh, we can conclude, so we started from the least significant bit, we can conclude that A is greater than B, regardless of whatever the result before, right? Because this bit position is greater than any previous bit position, right? So since A is greater than B here, okay, we know that this is sufficient for us to produce a what? A greater than signal, that is 1. Okay, and a less than, an equal, that is 0, of course, and less than, that is 0. Okay, let me add another sorry, another case. Let's say 0, 0 here. Okay, and then 0, 1. Okay, so now I get, so far so good. Is it clear? So is it clear why we get a 1 here? Because why? Because so far the number A is greater than the number B, right? By just looking at this position. Yeah, this position has a greater value than any previous position. So this one is greater than this one. Okay, so I must conclude that my GT is 1 here. Okay, now for the next stage, any question, or shall I continue? For the next stage, I'm going to assume that you guys are good. For the next stage, I have a 0, 0 for A and B. Okay, for the next stage, I have a 0, 0. So can I use this information regardless of whatever before? Can I use this information here to conclude what are the values of the signals?
No, you can't.
You can't. Why is that?
Because in the previous it was A bigger, so you have to, since they are equal, you have to pass it. So
Excellent.
A is still bigger.
Excellent, excellent. Okay, so since they are equal here, I must take my decision from before, right? If equal was the case, then they will be still equal, okay? If greater than was the case, then I should pass it. If less than was the case, then I should pass it, okay? So I'm going to pass here, what? A 1 here, and a 0 here, and a 0 here, okay? And then I get a less than here, okay? Right? Less than, because this is the most significant bit now. This is the most significant bit. And since the most significant bit here is less than of A is less than the most significant bit of B, we know that regardless of the previous information, we know that the two numbers will be, I mean, A is going to be less than B. So the result here is going to be 0, 0, and 1. Okay? So notice that the cell here inside, okay, takes whatever input that is coming in from here and whatever bits that are coming and produce the result. Notice that each one of these cells is the same, okay? It is processing, it is producing the same thing, okay, over and over. So these are copies. The only thing that is different is the input, okay? So we just design one cell and then cascade it to get the in-bit comparator, okay? So coming back, any question before I come back here? Come back to the theoretical part? Any question about the example? Okay, coming back to the iterative design of the comparator. Okay, so we must design a cell that accepts AI and BI, and also it accepts the previous state of comparison, GTI minus 1, EQI minus 1, and LTI minus 1, and produce three signals, GTI, EQI, and LTI. Okay, and then cascade it to get our n-bit comparator. Here it is 4-bit comparator. Okay, notice that initially we get a 0, 1, 0 because we assume that the numbers are equal, and then prove that they are equal or disprove. Okay, so all these cells have the same internal structure. How do we know how to do it? Okay, so we just need to now define each one of these signals, okay, from our observations, okay, from our examples. Okay, so we know that EQ will be 1 if and only if the previous EQ is 1, meaning that all the previous bits are ones, are equal. Okay, all the previous bits of A and B were equal, and the current bits are equal as well. If this is the case, then my EQI will be 1. Okay, so EI is 1 means that the current bits are equal. Okay, so my EQI is nothing but EQI minus 1 ANDed with AI XNORed with BI. Clear? Then we have GTI. GTI is going to be 1 if and only if AI is greater than BI. In this case, regardless of whatever the state before, okay, then GTI will be 1. The other case in which GTI will be 1 is when you have equality from before, okay? I mean, equality now and GT from before, okay? Equality now, okay? So EI is going to be 1 and GT from before, just like we saw in the example. Okay, so my GTI is going to be AI BI complement. This is AI is greater than BI, or with EI into GTI minus 1. Okay, so I can just replace this with the full expression here, BI complement, or with AI XNORed with BI and ended with GTI minus 1. Okay, and then LT, similarly, LT will be 1 if and only if AI is less than BI. That's one condition. The other condition is that so one of them will be sufficient to have LTI equal to 1. The other condition is that AI equals BI, and we have a less than from before. Okay, so this is the case for LTI, and similarly we can change this to AI complement BI ORed with ORed. Okay, AI XNORed with BI ANDed with LTI minus 1. Okay, so this is simple. Okay, these are the circuits. Okay, we have EI, which is used by all other gates, all other components. Okay, EI is used, so I calculated it here. Okay, and the blue one is for the equality here. Okay, this is the blue one. It's just an AND gate. Okay, and the green one here is GTI, and the red one is LTI. Okay, just like we did it from the least significant bit to the most significant bit iteratively, notice that you can do also the reverse. which is from the least significant bit, or from the most significant bit to the least significant bit, iteratively as well. Okay, so I encourage you to try to do that yourself. Okay. All right. If no questions are there, I'm going to move on to the next subject. Otherwise, please ask. I'll just wait for 30 seconds and then move on.
Doctor, what is the benefit of using one of each these different approaches?
Okay. So excellent question. So notice here that, do you see the design of the cell here? How many
Yes.
gates? How many gates did we use? A cell, each cell with 1, 2, 3, 4, 5, 6, 7, 8. Okay. I mean, plus some inverters, of course. Yeah.
Yes.
So 8 gates. Okay. This is for the whole cell. Okay. And so our cell is composed of 8 gates only. However, for this design, you can see that less than is this horrible expression. Okay. And greater than is this other big expression here. You see that? It's bigger. Okay. So we are taking a gigantic step here to calculate GT and LT as well as EQ. So if I just expand this into this expression, you'll see that EQ is also big. Okay. However, here we have this is a disadvantage of the first approach. Okay, the first approach produces complicated expressions for each signal, each output signal. The second approach, okay, produces a much simplified signal for each output of the bit slice. Okay, this is an advantage. Okay, it's more manageable and very so if you have a bug, you can catch it easily, more easily than the bigger expression. However, eventually you are going to use you're going to use a staged design, right? So you have what we call cascaded design. So in general, the number of gates will be comparable, but the only difference is that the first approach of design is almost a two-level design, whereas this design is a multi-level design. So you can also infer a problem with what we call the delay of this design. Okay, the delay. This design has a greater delay than the other design. Okay, because the signal has to propagate from here all the way to here. So imagine that you have a 64-bit comparator, magnitude comparator. You need to wait for 64 deltas, okay, where delta is the propagation delay from here to here, okay, to get the correct output eventually at the output of the comparator. Okay, is this clear? Yeah. Who was asking?
Yes. Thank you. Yeah, I understand now. Faisal.
Okay, excellent. So now you get the let's say that you get a design. Okay, you want to design. We just constructed the cell, okay, which is 1-bit cell comparator, and we would like to use it like in a 3-bit comparator. How do we do that? We just cascade the design. That's it. Okay, so we have here a 1-bit comparator that is connected to A0 and B0, and in this case, the initial condition, the initial values of greater than, equal, and less than, we feed it with 0, 1, 0 because we assume that the two numbers are equal, and then we cascade the signals for the next cell with A1 and B1, and then the next cell, which is A2 and B2, and then this is our final output. Okay. So these are the inputs of the comparator, plus these are the outputs. Okay. So these are fixed inputs. They don't change. They never change. Okay. So you can consider them as I mean, if you want to design your no, actually, no, you can't. If you want to design it using a K-map, then you have a 5-variable K-map. You cannot just assume that the other conditions are not there. But if you want to use a K-map, then there are some don't care conditions, right? Who can tell me some don't care conditions for the bit slice?
When the greater than or equal are both, for example, 1.
Excellent. When you have more than one or no ones at all, these are don't care conditions. Okay. It's only so even though for the cell for the so how many valid, let's say how many valid conditions, it's easy to calculate. We have three valid uh, uh, combinations for the three signals, three valid combinations. So it's either 0 0 1 or 0 1 0 or 1 1 0 0. This is for greater than, less than, and equal. And we multiply this by 4 valid inputs for A and B, right? Which is 0 0 0 1 and 1 0 and then 1 1. Okay, so how many inputs do we have in our truth table? Basically, it's
12.
4 times 3, which is 12. Yeah, excellent. So the truth table of the cell is much more manageable, even though you have to, in the K-map, you need 5 variables K-map, okay? But we didn't need the K-map anyway. We just did it using logic, okay? So excellent. Any other question? Okay, moving on to the, actually, before I move on, so I want to talk about the black box design of the ripple carry adder and magnitude comparator. So both components can be looked at or viewed as black boxes, okay? And we can use these black boxes to construct larger circuits, okay? And in the black boxes, we just hide the details. So we say for a 4-bit ripple carry adder, or a 4-bit adder here, yeah? We have a 4-bit adder and then a big box that accepts A and B, where A is 4-bit, for example, and B is 4-bit. That's why the adder is a 4-bit ripple carry adder. And Cn is just 1 bit, so that you don't have to say 1 here because the 1 is the default size of a wire. And then you have S and a C out, okay? S is 4-bit and C out is 1 bit. Okay, so this is a black box representation of a 4-bit ripple carry adder. Okay, so when we say use a 4-bit ripple carry adder to implement some functionality, you can use it like this. You don't have to draw the inside function, the inside circuit of the 4-bit ripple carry adder. All you need to do is to what we call annotate your black box by writing its function, okay, and then annotate the inputs and outputs and their sizes, okay. So although this input is A, maybe the external input may be different. Maybe it's called X, okay. So do not confuse this when you see it later, okay. So X is the external signal and A is the internal signal, okay. Like just Verilog, okay. In Verilog, you have a port definition, okay, and when you instantiate, you have a different name for the signal, okay. So the external signal can have different name for the port signal, okay. Similarly, for the bit comparator, for magnitude, I mean for the 4-bit magnitude comparator, we have A and B, okay, and then we have the 3 signals: A greater than B, A equal B, and A less than B, okay. Notice that A and B are 4 bits, for example, and then that's the comparator is called 4-bit magnitude comparator. And notice that we do not include these as part of the black box because they are details, okay, and they're just fixed values, okay. The rest is internal to the circuit. We don't show it, okay. So this is a black box or a symbol for the magnitude comparator, okay. All right. Having said so, this concludes our discussion about the magnitude comparator as well as the ripple carry adder. We will come back to the ripple carry adder when we discuss negative numbers. I mean signed integers as well, to construct a subtractor from the adder. Okay, but for now we have just finished that, and we will move on to another design technique, which is called design by contraction. Okay, and this technique, okay, please pay attention because it's simple. The technique is extremely simple. Okay, it's based on simplifying the circuit based on forcing the input to a certain value. Okay, so you have a big circuit and you want to force some of the inputs to a certain value, and then you see what is the resulting circuit, the equivalent resulting circuit, the simplified version. Okay, so this is called design by contraction because you are contracting the design, or the number of gates in the design. Okay, so let's take an example. We would like to design a 4-bit incrementer that increments by 1, of course. Okay, by contracting a 4-bit ripple carry adder. Okay, so we know that the ripple carry adder is this one here. Okay, and to design an incrementer, for example, if we have an input A and we would like to produce an output A plus 1, then what is the alternative here that we can do? Either have what? I'm going to give you one option and then you give me the other option. Okay, either have C1 as 1 and B as 0. Okay, and then get the output as A plus 1, right? The other alternative is, who can tell me? What is the other alternative? So the objective here is to use the 4-bit ripple carry adder to produce an incrementer. And I told you that one of the options is to set Cn to 1 and B to 0. Okay, producing A plus 1 here. What is the other alternative that you can do in order to implement A plus 1 other than setting Cn to 1 and B to 0?
Setting B to 1 and Cn to 0.
Excellent. Yeah, this is the other alternative. But we do the alternative that I said because it's going to simplify our circuit. Okay, simplify our circuit. So basically what we do is set B to 0 and Cn to 1. This will give us A plus 1 at the output. Okay, so we start with the design like here. Okay, this is the ripple carry adder from internally. Okay, yeah, and then substitute B, the B as 4 zeros because it's B is 0. Okay, and Cn with 1, right? So we get this now. Okay, so let me ask you this. What is the output here?
A1 XNOR 0. A0 XNOR 0.
Which is, using the properties of the XOR, A0, right? Anything XORed with 0 is the same thing. This is A0, all right? And then A0 XORed with 1 is A0 complement, okay? Remember the XOR, the exam is approaching, guys, so please make sure that you review, okay? A0 complement is S0. So the whole thing here reduces or contracts to just nothing but an inverter, right? So the S0 is nothing but A0 complement, okay? What about this signal here? This is going to be
0.
0. So no need for this because it is feeding an OR gate, and 0 is the identity of the OR, right? 0 is so meaning that this OR gate is not required. Yeah. What about
Yes.
the output here?
A0.
A0, so no need for this AND gate as well. Okay, so the whole thing here is an inverter. Okay, this is S0, and then you take A0 and feed it to as C1 now. So and at C1 we have A0. Okay, at C1 we have A0. So this is the annotation here. Okay, so we didn't need this, nor this, nor this, nor this, nor this. Okay, so the whole thing here will become an inverter. Okay, A0 complement, and then this one will become A0. Okay, by the same discussion, we can cancel this OR gate and get A1 here. Okay, so we have A1 here and A0 here. So S1 will be A1, A0, XORed with A0. And this is not required because the output is 0, and this is not required because one of the inputs is 0. So whatever is in here, it will be bypassed to the output. Okay, so this is A1, A0, A0. All right, and you can see that for the next stage, it is going to be the same. Okay, because this design is iterative. Okay, so this is going to be XORed with A2, and then this is going to be ANDed with. So eventually we will get rid of this, and then here this. Okay, so eventually what you will have is nothing but this design left. Okay, so here you have an inverter, and then you take this and XOR it with A1, and then you take these two and AND them together and XOR the result with A2, and then you take this and AND it with this signal here, and the result is XORed with A3 to get S3, and then you take this and AND it with A3 to get C4. Okay, so this is called design by contraction. And if you're not really comfortable with that, you can also do it using Boolean algebra. Okay, using Boolean algebra. So how do you do it using Boolean algebra? Okay, I have done it here. Okay, but let's just do it together quickly. We know from before that let's just, we know from before that these are the outputs of the full adder. Okay, if you have been reviewing so far, you'd have known that. Okay, let me just erase everything, and then I'm not going to do all of them. So if you have been reviewing, okay, you'll know that SI of the full adder. So we have a full adder. Let me make it bigger so that give myself some space. And we have AI, BI, and then we have SI and C out, and we have CN as well. These are the two outputs, SI and C out, and these are inputs. All of these are inputs. So we know that SI is this expression here. Okay, from here. Okay, you can see that S0 is A0 XORed with B0 XORed with CN. Okay, this is the expression. Okay, and CI plus 1 is going to be this expression here. Okay, which is this ANDed with this, ORed with this, ANDed with this. Okay, take the OR and you get your CI plus 1. Okay, now it is easy to see that my S0 is going to be just substitute. Okay, A0 XORed with B0 XORed with C0, which is A0 XORed with what? 0 XORed with 1, right? Because I've set my B to zeros and my C0 to 1. Yeah? What is this now? Using XOR properties, it is A0 XORed with 1. So you just got rid of this 0 here, okay? And this is nothing but A0 complement, okay? And if you're not convinced about this, use the XOR definition, which is A0 complement ended with 1, ORed with A0, ended with 0, ended with 1 complement, okay? Which is what? A0 complement, okay? You see that? Is this clear? So now we proved that S0 is correct here, okay? S0 is nothing but A0 complement, okay? What about S1? In order to calculate S1, you need C1. What is C1? We can use this formula to calculate it, okay? C1 is going to be what? A0 XORed with B0 ANDed with C0 or with A0 B0. Yeah? And that is what? A0 XORed with 0 ANDed with C0, which is 1, ORed with A0 ANDed with 0. And that is equal to what? A0. Yeah? Haven't we saw that C1 is A0 from here? Yeah? A1 is indeed A0. So this is A0, okay, ended with 1, okay, and we have a 0 here. So we have A0 ordered with 0. So this is C1. C1 is A0, okay? Next, we can calculate S1 now. S1 is going to be A1 XORed with B1 XORed with C0. C1, I'm sorry. Yeah? Substitute now. This is going to be a 0, and this is going to be A0. So this is A1 XORed with A0. Yeah? Isn't it the case here? S1 is A0 XORed with A1. I can sense confusion here, but I'm not sure because I'm not receiving any feedback. Are you following, guys?
Yes.
Any question or confusion, or can you get S2 by yourself, for example? Who can tell me what is S2 from here? How can I get S2? Using Boolean algebra. Now let me just erase this because we don't need it anymore. Okay, so S2, in order to calculate S2, we need what? A2 XORed with B2 XORed with C2. But we need this in order to calculate it. And this one here, C2, is going to be A1 XORed with B1 ANDed with C1 ORed with A1 ANDed with 0. Okay, sometimes so B1 is 0 as well here. So this is nothing but A1 ANDed with C1. What is C1 so far?
A1?
A0.
A0. A0, yes.
A0 ORed with 0. Okay, so this is my C2. And my S2 now becomes what? This is going to be a 0 XORed with C2. So I have A2 XORed with A1 A0. Okay? So if you check S2, you'll find that it is indeed A2 XORed with A1, A0. Okay. Well, S2 is nothing but A2 XORed with A1, A0. You see that? So you can do it either using Boolean algebra, or you can, if you're also comfortable with the graphical method, then it's fine. But it requires a lot of drawing as well. Okay. Anyway, any question about this? I'm going to be quiet for some time so that you guys can think of a question or something. Okay.
Doctor,
Yes.
when we choose B1 to 0 and CN to B1, we limit the inputs.
Ripple carry
Like,
adder. We limit the ripple carry adder, right?
Yes.
Yeah, that is the case. That is the, remember that the objective here is to design a 4-bit incrementer. All we need is a circuit that receives A and produces A plus 1.
Okay.
Yeah, so this is the reason. So we're using a 4-bit ripple carry adder. Okay, we are contracting the design of a 4-bit ripple carry adder to come up with a 4-bit incrementer. You must understand the big picture in order to appreciate this design method. Okay. So this design methodology can be used anywhere if you want. I mean, you can use any circuit that you know will is generic enough. Okay, how can you do an increment by 2, for example? Increment by 2 can be done by forcing
B to 2 and C to 0.
Or B to 1 and C to 1, and so on and so forth. You have these two possibilities, and how to implement increment by 3 maybe. So whatever is there. I mean, you could have a question like this: derive an incrementer by 3 using a design by contraction of a 4-bit ripple carry adder. Maybe. Okay. So just think about it and give yourself some time to think about it, and do some exercises yourself. Okay. Sometimes it's a good thing to ask yourself questions. Okay. Ask yourself a question and try to solve it yourself. This way you'll feel satisfied. Okay. Challenge yourself by designing a problem and solving it yourself. I mean, this is an excellent, if you, for example, come up with a problem and you cannot solve it, come back to me and I'll be glad to help. Okay. So this will, in fact, excite you and then make you involved with the course. Okay. I'm going to stop here. Let me stop recording. And next time we'll talk about signed numbers.